Here's an instructional video that is tackling number 15 in our sampling assignment for Chapter 12. At 1 atmosphere, how much energy is required to heat 39 grams of solid water at negative 12 Celsius degree to gaseous water at 119 Celsius degree? And our final answer will come out in kilojoules. So we had practiced some of these in first semester and kind of get an idea of the phase change involved. We are starting at negative 12 degrees as our first provided temperature, and we have to go all the way up to 119 degrees Celsius. Other interesting temperatures, we know that at 0 degrees, water will undergo a phase change, and at 100 degrees, water will undergo a phase change. So we have some line segments to consider. We start by warming and providing heat energy to warm the solid ice up to 0 degrees. We know that this particular line segment will be an MC delta T problem, where solid water is gaining energy simply by warming up to 0. We undergo a phase change in which the solid melts and becomes a liquid. We know that is the delta H of fusion. Here we have warming again, where we have an MC delta T problem. It will undergo a phase change where we have the liquid turning into a gas, and then the final line segment will be warming again the gaseous water up to the 119 degrees. So we have line segment AB, line segment BC, C to D, D to E, and E to F. So the other provided example here, the information I had to click on to pull up, or to look up these constants. So we're given either per gram or per mole, our choice. And really, so we're given mass. Maybe we should just use this column and not have to worry about doing a mole conversion. If we wanted to do a gram into mole, we would then go to this column, but I'll just stick with the first one since the given answer is in a gram. We'll go to work starting down here. We have line segment AB. We want to calculate the heat energy required to warm up solid water from negative 12 to 0 degrees. So the mass given to me, we know was 39 grams. That'll be repetitive here, 39 grams. We want to find the specific heat of solid water given to us in a joule per gram Celsius, and that's at 2.087 joule per gram Celsius. And I'm just making sure I have like units. And the delta T from negative 12 up to 0 is going to change by 12 degrees Celsius. And when I get this provided answer, it will come out in a joule. So I'm going to just simply divide by 1,000 to get a kJ of energy. In line segment BC, we undergo a phase change from the solid melting. So we know that the delta H of fusion is what we need here. And the delta H of fusion is given to us right here in the first line. And again, I'm going to grab it in a gram unit to just be sure that we have like units. We had 39 grams in my story problem, and I'm simply going to multiply by 333.6 joules per gram, the amount of energy needed to melt a gram of ice. And I'm also going to simply divide by 1,000 to make sure my joules converts into a kilojoule, so at the end I can add like units. Line segment CD, remembering where we're heading? Now we're climbing up here from line segment liquid water 0 to liquid water at 100 degrees. So we have an MC delta T problem. Our 39 grams of liquid water, specific heat of liquid water right here, we know that probably by heart by now, 4.184 joules per gram Celsius. And from 0 to 100, we know that that line segment is 100 units. Let's divide by 1,000, forgot that there for a moment, to land in a kJ, our desired unit. Line segment DE, Remember where we're at now? We're going to be using the delta H of vaporization. Moving from liquid to gas is the process of vaporizing. And again, I'm using the per gram. So the delta H of vaporization in that particular line segment are 39 grams multiplied by the constant of 2257 joules per gram. Remember, I'm going to divide by 1,000 to get that desired kJ unit. And there is one more line segment in which we're going to warm up that gaseous water a little bit further. Same amount, 39 grams. How about the specific heat for steam, exactly given as 3 sig fig, so 2.000 joules per gram Celsius. And I have to go back and take a peek. We started at 100 and we're climbing to 119, so that line segment is 19 units long on our y-axis, delta T of 19 degrees. Report out in a kJ to simply add like units. Well, it's a bunch of calculator work now, isn't it? So let's start with, and hit with me because I know I make mistakes, 39 times 2.087 times 12. Divide by 1,000. And this answer I'm finding to be 0.9767. Line segment 2, 39 times 333.6. Divide by 1,000. 13.010. 39 times 4.184 times 100, divide by 1,000. 16.3176. Next line segment is 39 times 2257, divide by 1,000. Most energetic line by far, 88.023. And the last line segment, 39 times 2 times 19, divide by 1,000. 1.482. And of course, the final tally is to simply add the pages or the line segments to get a total kJ. So beginning with the first line segment, we had 0.9767 added to 13.010 plus 16.3176 plus 88.023 plus 1.482, and that's a grand total of 119.8093. How many sig figs should I consider in my problem? We had just one decimal point given throughout. The only difference, my friends, as you work your sapling might be the amount that you started with and the temperatures that you're landing to, but the process will indeed be the same. I hope you found this video helpful.